All right, thanks, Howard. As you said, my name is Steve Moore. I'm with ATL. I'll be presenting cold weather concreting today. Go ahead and get started. Here's our topics. First topic, I'll do a little introduction on concrete, the bread of the construction industry, as I like to call it. I didn't coin that phrase, but I like it. We'll talk about some essentials of quality concrete. Then we'll get into the meat and potatoes of it, cold weather concreting. It's really based on two ACI documents that are out there, and I encourage people to read them and use them for reference. They're both great documents. ACI 306R, which was readopted in 2016. That's the guide to cold weather concreting. As the name implies, it is just a guide. But there's a whole lot of really good information in there. A lot of research has been done to gather that information, and it's for public use, public knowledge. The next document is 306.1. Those are the specifications, the actual specifications that ACI publishes that can be used and incorporated in projects. And then towards the end, we're going to talk about the maturity method, ASTM C1074. That maturity method is a way of estimating in-place concrete strength, non-destructive way of estimating in-place concrete strength. We'll talk about the theories and principles and how that can be applied to one of your projects in the field. So as I said, the bread of the construction industry, that's what we call concrete. I can't take credit for that term, but I like it. You know, when we think of bread, we kind of think of it as a dietary staple. And concrete for construction projects really is a staple. Concrete's the second most widely used substance in the world, next to water. So there's a lot of it that's used and placed every year. There in front of you, you've got some different proportions. You know, this is just one particular mix. This is just an average, 6% air, 11% Portland cement, or some other cementitious materials. We're seeing a lot of other replacements, fly ash, silica fume, things like that. 41% gravel, crushed stone for your coarse aggregate, about 26% sand or fine aggregate, and about 16% water. Obviously, those are by volume because air has no mass, or at least for our purposes, it has no mass. So each mix is going to be a little bit different. I'll talk about that a little bit. Some mixes have got air, some mixes don't. But just for some general round numbers, those are pretty good. You know, if you notice, about 2/3 of the mix by volume is the aggregates, just kind of taking up space. And we'll talk about that a little bit more as well. 5 essentials of quality concrete: suitable and compatible materials. There's a lot of chemistry that goes into concrete and the hydration of cement and all those materials interacting, although there's not a lot of materials in there. You know, all those materials interacting amongst each other. You know, we want to make sure that they're playing nice and that they're all compatible, along with whatever admixtures might be in your mix also. Some admixtures are not compatible with other admixtures. So that's something that maybe you want to keep in mind. Proportioning, mixing, transporting, transporting probably one of the things that people don't think about very often, but obviously proportioning and mixing. You know, the previous slide had some rough proportions on there. Again, each mix is going to be a little bit different depending on the application, but you want to make sure it's proportioned properly, certainly mixed properly, and transported properly, and that's not only transported properly, but take into consideration the time of transport, and maybe you want to account for longer transport times or maybe longer placement times in your mix, and maybe add a set retarding admixture. You know, if your transport time is pushing 60 minutes or more, you know, it doesn't always give you a whole lot of time to place the concrete once it gets to the job site. Placement is the next thing, placing and consolidation. Obviously, you want to make sure it's placed properly, consolidated properly, vibrated, so that you know it's you know you're getting out all of the you know, large air voids, things like that, so it's not honeycombing. Making sure that you're getting good consolidation around your reinforcement, especially if you've got dense, you know, if it's a densely reinforced structure, columns, maybe tall foundation walls like wastewater treatment plants or you know, sludge lagoons or something like that. You know, want to make sure that it's consolidated properly. Finishing and joining is next after it's placed and consolidated. We don't just get up and walk away. You got to make sure it's finished, jointed. You know, that certainly comes into play mostly in flat work. You know, slabs that have a lot of exposed surface area, want to make sure it's finished properly, jointed properly for shrinkage. Concrete shrinks. We all know that. We just want to control where that's going to happen. And then after all that's done, we got to make sure that it cures properly. Let it sit there, make sure it's the right temperatures. We're going to be talking a lot about temperatures, specifically colder temperatures. There's another presentation that we give a lot of times late spring, early summer, that talks about hot weather concreting, and you know, obviously temperatures are important at that time also. So, you know, my opinion, any one of these five items, if you don't have it, you know, maybe your concrete's not going to fail, but you're probably not going to get the quality and the durability out of your concrete that you want if some of these items are missed. So how does ACI define cold weather? They've got a couple of different definitions depending on what document you're looking at. ACI 306.1, which again, those are the specifications, those are the ACI specifications for cold weather concreting. They defined cold weather as 3 consecutive days of average temperatures below 40 degrees and less than 50 degrees for half of any 24-hour period. So both of those conditions have to be met for it to be considered cold weather by ACI specifications. The average temperature is just taken as it's the arithmetic mean. We know whatever the high is, whatever the low is. And then you figure out the average between the two. It's not weighted by time or anything like that. It's just the high and the low. ACI 306, which again, that's the guide to cold weather concreting. Their definition of cold weather is whenever the air temperature has fallen to or is expected to fall below 40 degrees during the protection period. 40 degrees is kind of a set number because below 40 degrees, cement hydration slows down significantly. Obviously at 32 degrees when water freezes, it stops altogether. But right around 34, 35, 36 degrees is when it really slows down almost to nothing. And you know, depending on some other factors, you know, between that, you know, say 35 and 40 degrees, we're getting very little cement hydration. So that's the reason for the 40 degree cutoff. Going to be showing you a number of pictures throughout the presentation. A lot of the pictures are from one particular project that we did here in the Albany, New York area. And as a side note, we probably have I know we've got a lot of people on the listening in here today. I've always wondered how far we're reaching out with these webinars. If you guys have a minute, maybe type in city and state or maybe country where you guys are at. Just kind of curious to see where everybody's coming from. So anyway, this one project in the Albany, New York area had a very accelerated construction schedule. They broke ground. Geez, I think they put the shovel in the ground the week between Christmas and New Year's, and a lot of the foundation work obviously was done during the winter time, January, February, which are kind of the coldest months of the year. And you can see, looking around in this picture, you know, you can see a bunch of things that are needed for cold weather. You know, obviously we got some blankets over here, some blankets here, but certainly proper planning is really the biggest thing for being prepared for cold weather concreting, and I'll mention that quite a bit. Here's another project. I believe I didn't take this particular picture, but I believe this is on the shores of Lake Champlain. This is just kind of the beginning phases of this project, but you can also see kind of a little glycol heating unit back here. You can see some of these glycol heating lines right here, and these are probably thermal blankets right here off to the side. So, you know, again, just proper preparation is really key if you want to place concrete during the winter time. And I mean, construction doesn't stop during the winter time. You know, we got a lot. You know, a lot of our months here in the Northeast and elsewhere, you know, we meet those cold weather requirements, you know, regardless of the definition. You know, we meet those cold weather requirements quite often throughout the year. So this is a way to keep the construction schedule going. So ACI 306, again, those are the guidelines. The main objectives: prevent early age damage due to freezing. We want to make sure our concrete's not going to freeze. Once it freezes, it just doesn't come back, or it rarely comes back. Want to make sure that we're getting adequate strength development, you know, during that initial protection period. Maintaining curing conditions that promote that strength development. We want to limit rapid temperature changes, which can cause cracks due to thermal stress. You can think of concrete as kind of like a ceramic material that's going to be susceptible to thermal stress and cracks. We want to make sure we're providing protection consistent with the design, so that we get that quality and durability of our concrete. You know, concrete can last, you know, decades, hundreds, even thousands of years. So we want to make sure that we're allowing that to happen by providing proper protection. So to prevent early age damage, again, you know, planning. You know, I can't stress that enough. ACI says about 500 PSI will provide one freeze-thaw cycle protection, and you get about 500 PSI within about a day or two. At curing temperatures of about 55 degrees. That's another temperature that you'll see somewhat consistent throughout some of this presentation is 55 degrees. But that 500 PSI, that's just one freeze-thaw cycle. Multiple freeze-thaw cycles, you know, at that strength, it's probably not going to hold up to that. So again, we want to make sure that we're protecting everything so that it can continue to gain strength. It's going to be very vulnerable during that critical saturation period where there's a lot of water in the concrete and the cement starting to hydrate. That 500 PSI that does assume that the concrete is air entrained. If you don't have air entrained concrete, you're definitely not going to get any kind of significant freeze thaw durability, regardless of the strength. So 306.1, again, these are the ACI specifications. They state that the concrete should be, actually it says shall be air entrained if the concrete is exposed to freezing and thawing during the construction period. That's pretty important to know. So, you know, this project I was talking about here in the Albany area, you know, when they're doing construction in the wintertime, they may have an interior slab that they're placing that during its service life isn't going to see any kind of freeze thaw cycles because it's inside. But if it's exposed to freezing and thawing during the construction period, it needs to be air entrained. Again, that's, you know, if it's not air entrained, it's not going to hold up to those freeze thaw cycles. So we want to make sure that that's something that is very often overlooked. Minimum temperature of massive embedments. We want to make sure that that it's not below 32 degrees. You know, concrete's not gonna bond well to frozen rebar. We want to make sure that it's bonding well to the reinforcement. And we want to make sure that the subgrade is thawed. We get any kind of frost removal from all the reinforcement. Thawed subgrade, do not want to place concrete, cannot place concrete on frozen subgrade, as ACI 306.1 states. So the subgrade should be thawed prior to prior to concrete placement, and that can be done a number of different ways. A couple more pictures from the project that was on Lake Champlain. These two pictures they're actually taking the curing blankets off of the subgrade because they had the glycol lines. You can see some of them right here. They had these glycol lines on the subgrade to make sure that the subgrade was thawed, and then they put the curing blankets over the glycol lines, thaw out the subgrade, peel the blankets back, peel those glycol lines back, and then place your concrete, and then you can put the lines and the blankets right back on the concrete. So this is a table out of ACI 306. It's table 5.1 from 306-10, but I think in 2016 they did reorganize some of the chapters in 306. So I think this might be in the new ACI 306. It might be 7.1, and it's kind of a condensed version of this table. But what we see here is it's got recommended temperatures. And again, remember, this is the guidance document. This isn't the specification. So these are just recommended temperatures, although these temperatures are pretty consistent in 306.1 specifications. But we can see that, you know, depending on our section size and minimum section size, you know, in this case, less than 12 inches. So this would be like, you know, say a 6-inch slab, maybe an 8-inch retaining wall or something like that. This dimension over here, 12 to 36 inches. So these are larger dimensions. But the minimum concrete temperature is placed and maintained for these smaller, thinner sections. We're going to keep that. We want to keep that at 55 degrees. For the larger ones, we can go down to 50 because we're using that. We're kind of using the heat of hydration, you know, from that larger concrete placement. You know, the larger mass concrete, although not considered mass concrete, but just the mass of the concrete. We can maintain these temperatures a little bit lower. So generally speaking, we're looking at 55 degrees. We don't see a lot of structures that are greater than 12 inches. So 55 degrees is kind of that magic number, placing and maintaining. So that's placement at 55 degrees and maintaining a 55-degree temperature during our protection period. The bottom part of this table has got mixed temperatures based on ambient temperatures. So above 30 degrees, mixed temperature should be 60. You know, minimum mixed temperature is 60 degrees. Larger, thicker placements, we can go down to 55 degrees. 0 to 30 degrees, we're at 65 degrees. Below 0, we're at 70 degrees. So that's the concrete mix. You know, that's as it's mixed. We want to make sure that we're maintaining, you know, that we have that 60, 65, or 70 degrees, you know, for our concrete. So again, we're talking about cold weather. You know, we could be, you know, anywhere from 0 to 40 or, you know, below 0 to 40 degrees. How do we get those temperatures in our mixed concrete? One of the easiest ways is to raise the temperature of the constituents that are in the concrete, right? You know, coarse fine aggregates, water, cement, you know, changing, you know, raising the temperature. So this table here is out of the is from the Portland Cement Association, and we can see the slope of this line. I didn't calculate it, but it's probably about a 2 to 1. So, you know, here we've got to the left, we've got mixed temperature rise. Here in the x-axis, we've got material temperature rise. So as we raise the material temperature of, say, the aggregates, you know, we're going to raise the overall mixed temperature. And again, remember, the aggregates are about 2/3 by volume of our concrete. So you get a lot of bang for your buck by raising the aggregate temperature. You know, again, about a 2 degree temperature rise will give you about a 1 degree overall mixed temperature rise. A little bit less for water because obviously there's a little bit less water in there, and even less for the cement. we don't have any admixtures on there, the admixtures don't really, there's just not enough of them to make a difference. But the point of this graph is just to show you that you can change the temperature, and the aggregate is the best way. So here we've got question number 1. It's a true or false question. ACI allows concrete to be placed on frozen subgrade. There should be a poll open in front of you guys right now. So answer true or false whether or not ACI will allow you to place concrete on frozen subgrade. All right, the answer to that is false. I hope everybody got that right. So I mentioned a protection period. Obviously, one of the goals of ACI 306 was to protect for strength development. This is another table out of 306. Again, this is 306.10. I think this is probably, I want to say, chapter 8 in the new 306. I keep this table in here because it's kind of a condensed table, and the new tables are just too big to they're too big to really see very well. So what we've got over here, we've got service conditions here on the left, and then on the right we've got protection period depending on whether or not our concrete is normal set concrete. If we've got accelerated set concrete, we're using an accelerator, non-chloride accelerators, right? We can shorten our protection period a little bit. What we've got up here, it says protection period at minimum temperature, line 1 from table 5.1. That line 1, that's the 55 degrees for our sections less than 12 inches, or 50 degrees for those sections between 12 and 36 inches. These service conditions listed here on the left: no load, not exposed. The load is actually during the curing period. So that's if you're going to be loading the concrete element during your curing period. So within 28 days, if you're going to put a load on it, you know, that's the service condition. It doesn't explicitly say that in the table, but when you read through the ACI document, that's what it states. Now this exposure, this is exposure during the service period. So the no load is during the curing period, and the exposure is during the service period. So normal set concrete, if we don't have a load on it, we're not going to put a load on it during the curing period during the first 28 days, and it's not exposed to freeze thaw during the in service. That would be something like maybe a foundation wall if you're not going to start, you know, putting up you know, column loads or wall loads along the foundation, and the foundation is below the frost level. Our protection period would only be 2 days. Again, we're going to be maintaining 55 degrees for 2 days. You got normal set concrete, it's just 1 day. No load and exposed, we've got a 3-day protection period or a 2-day protection period with accelerated set. Partial load and exposed, we've got a 6-day protection period, or 4 days for accelerated set concrete. Partial load exposed, that's certainly not uncommon during construction. No load and exposed is certainly not uncommon. So protection periods between 3 and 6 days are probably the most common. I'll urge everyone to make sure they read through the project specifications. These are recommendations in 306 for strength development. So these are recommendations. Your project specifications may be a little bit different. I know here in New York State, the DOT has got different protection periods for some of their structures. So it's not that 3 or 6 days. So just make sure you're reading through the project specifications. This last line here, full load, if you're going to have a full load on your concrete element during the protection period, it says to see Chapter 8, and we'll address that here shortly. So another table in 306 is this table 7.3, and this is minimum exposure temperatures for concrete slabs above ground and walls for concrete placed and surface temperature maintained at 50 degrees for 3 days. So that's our protection period is 3 days, and we're maintaining 50 degrees for 3 days on walls and above ground slabs. We've got different portions of this table. So here on the left, this is our wall or slab thickness. So we've got anything from 6 inches to 60 inches, and then each one of these columns corresponds, or this set of columns corresponds to a concrete mix with 300 pounds of cubic yard. 300 pounds of cement per cubic yard. This one's 400 pounds of cement, and this one here is 500 pounds of cement per cubic yard, and that's what I've kind of highlighted here. I'm going to go to the next slide. It kind of blows this up a little bit more. This is a great table, by the way, especially for contractors. So here we've got minimum ambient temperature allowable when insulation having these values of thermal resistance is used. So these are the air temperatures right here. Again, this is our section thickness, or 6 to 60 inches. And these columns here correspond to different R values. So all of these columns are for R value 2, R value 4, and R value 6. And these are the temperatures, the air temperatures that it can get down to and still maintain a 50-degree temperature. What we're doing here is we're using the heat of hydration of the cement, and there's been a lot of research done into the heat of hydration. We're using that heat of hydration, we're capturing that heat, we're not going to let it out using these different R values to make sure that we're keeping our structure at that minimum temperature. So what I'm showing here with this arrow is a 12-inch wall, and we're expecting temperatures to get down to 3 degrees, which, by the way, is about as cold as that local project got when I was taking some pictures. We need an R value of 6, which isn't much. So again, this is specific to 500 pounds of cubic cement, or 500 pounds of cement per cubic yard, that particular wall thickness, this air temperature, and these R values. And again, we're using the heat of hydration to make sure that our concrete temperatures don't decrease. Those R values of 6, you're probably asking yourself, well, how do we know what R values we have? Our good old ACI 306 gives us some information on that. So here we've got R values of 1 inch for the following materials: expanded polystyrene, polyurethane, glass fibers, mineral fiber board, plywood. So if you think of your say about 3/4 inch plywood formwork, we can get about an R value of 1 just from the 3/4 inch plywood formwork. And then we put a couple of blankets on it. Maybe we get some blankets that are 1 inch thick or something like that. We're getting pretty close to our R value of 6. And one thing to note is most concrete blankets have tags on them that state what the R value is. This tag right here will tell you what the R value is. This obviously isn't 1 inch, so it's not going to have an R value. Mostly mineral fibers and these fiber boards. These are the two most common, materials inside the blankets. They're not 1 inch, so you're not going to get an R value of 3, but you get an R value of maybe 1 or 2 or something like that. Maybe some thicker blankets. This one's a little bit thicker. These two, these here. But again, the R value is typically on these tags. Now, that's not to say that these tags haven't been removed or have come off over the years, but take a look at them, and it'll tell you what the R value is usually. So here we've got question number 2. It's another true or false question. ACI 306.1, again, those are the ACI specifications, requires concrete that will be subjected to freezing during the construction period to be air entrained. True or false? I think I'm going to get some Jeopardy music and start to play Jeopardy music during this.
Go ahead, Steve.
Thanks, Howard. The answer is true, yes. Must be air entrained if it's going to be subject to freezing and thawing during the construction period, regardless of its in-service exposure. Here's another picture from that local project. Here we see contractor is very well prepared. We got this heater here blowing into here. By the way, they're just heating this enclosure. There's no concrete in here. Having this warm forced air is sometimes not the best thing. But you can see they got these blankets. They're tied up pretty good. They got a whole stack of blankets over here. They got a whole stack of blankets over there. This contractor was very well prepared. It was in the single digits when I was out here. These pictures were taken over the course of probably two to 3 weeks. Yeah, it got pretty cold. Here's a pier that was placed. You can see it's got blankets, multiple layers of blankets stacked around, tied up really well. These corners are really susceptible to, freezing and thawing or getting exposed to freezing. So they got the corners tied up really well. Basically, they just took the blankets that they were using for this footing and moved it up there. But again, taking a look around, this is a picture. This is the location of the previous picture. But you can see they got blankets, no glycol heaters around here. But you can see one over here. That's a glycol heating unit back over here. Long wall with blankets. Again, wrapped up pretty good. You can see this heating line coming in. I don't know, this might be a return line, some other lines coming in here. But point being, they were prepared. I believe this is a Mohawk River right along here. Yeah, lots of blankets, preparation, heating lines. Here's an aerial picture, give you an idea. The previous picture was taken, me standing right here. This is a Mohawk River. They started taking the blankets off of this one. But you can see orange blankets all over the place. They got this glycol heating unit right here. So these lines going out here, and they even got blankets covering the heating lines. So they're not losing any heat when it's going over to, wherever they want to heat it. Blankets all over the place, heating lines, very, very well prepared. So the next thing we want to do, we know what our protection period is. We know how to protect it depending on the concrete mix, exposure temperatures. Now we want to make sure that we're cooling it gradually to make sure that we're not introducing any thermal shock. Remove the heat slowly. Maybe turn the glycol heaters off, leave the blankets on. Maybe you remove one blanket at a time, remove them slowly. What this particular contractor did is they had so many of them, they just left them in place until they needed them. They went back to their oldest placement. they took blankets off of that placement and then used them on the new placement. But you want to make sure that you're avoiding rapid temperature changes. This table here kind of identifies, what the allowable temperature drop is in a 24-hour period after the end of the protection period. So we've already protected it for our, 3, 4, 6 days or whatever that requirement is. Again, kind of going by minimum section size. We don't want a temperature, if our sections are, less than 12 inches, again, this is our, 8-inch, 10-inch, 12-inch walls. We don't want to have more than a 50-degree temperature drop in a 24-hour period of time. Larger sections actually have a tighter requirement because on the inside, you're going to have a lot higher temperatures than you're going to have on the outside, and you don't want to have those huge temperature variations between the interior and the exterior of your concrete. That's really going to cause, or could potentially cause, some of that thermal cracking that we want to stay away from. So just know that we need to control that temperature drop over the 24-hour period. Oh yeah, and here's question number 3. Do we need to control the rate at which we allow the temperature to drop at the end of the protection period?
Go ahead, Steve.
And the answer to that obviously is yes. We definitely need to control the rate to make sure that we're not inducing any thermal shock into our nice freshly placed concrete. So this is a table that we saw a few slides ago about estimating, about full loads. If you're going to put a full load, again, this is during the curing period. It says see Chapter 8. Basically, what Chapter 8 says is that you need to do some sort of testing to verify the strength of that element if you're going to put a full load on it. They give you a couple of different ways to do that. Field curing cylinders, if you're going to field cure cylinders, which, by the way, we actually field cured cylinders on this Albany project, the pictures I've been showing you, but we tuck those cylinders up underneath the blanket so you can't see the cylinders, but that's where they are, and that's where they need to be if you're going to be using field cure cylinders, for this purpose. But one of the other things that Chapter 8 says, or one of the other methods, is you can use the maturity method. And the maturity method is a way of estimating concrete strength based on curing times and curing temperatures. So the primary concept here is not difficult to understand. You got a given combination of curing time and concrete temperature results in a specific strength for a given concrete mixture. That's easy enough to understand, right? I mean, concrete strength is a function of time and temperature. I think most of us probably know that and can easily understand that. And also, cold concrete develops strength much slower. Again, right around 35 degrees or slow, it almost stops completely. So we've got 2 different concrete maturity functions that we can evaluate. One is a time temperature factor. This is based on the Nurse-Saul equation, but Saul back in 1951, this is a statement he made: concrete of the same mix at the same maturity, and maturity is simply a product of the temperature and time, so temperature multiplied by the time. Has approximately the same strength, whatever combination of temperature and time go to make up that maturity. Again, it's kind of a fancy way of saying that the strength is a function of time and temperature. So here's the Nurse-Saul equation. It's, if you look at this, it's basically, it's a formula for area under a curve, right? M of t, this is your time temperature factor at age t. Delta t, that's your time interval. Normally, when we're doing this maturity testing, we're looking at either 1 minute or 15 minutes, depending on how long we're carrying out the test. So this delta t is usually a 1 minute or a 15-minute interval. T sub A is the average temperature during that time interval. So we know what the temperature is, during that, 1 minute or 15-minute time interval. T sub 0 is the datum temperature, which is essentially the temperature when strength development stops. There's different ways you can figure this out. The ASTM gives you a way to figure it out using 2x2 cubes, 2-inch by 2-inch cubes, just with a cement and water, and then you break those cubes. A lot of people, and the ASTM allows for this, a lot of people just use this a set temperature, 34, 35, 36 degrees, something like that, because we know that's about when strength development stops or gets really close to stopping. So that datum temperature a lot of times is 34, 35 degrees. But this is the equation. Again, it's just a summation of all of the different time intervals and the temperatures. There's another maturity function that's called the equivalent age factor. It says a number of days or hours at a specified temperature required to produce a maturity equal to the maturity achieved by a curing period at temperatures different from the specified temperature. An easy way of saying that, or something that's analogous to that, is comparing concrete cured in the field at different temperatures, right? The temperatures fluctuating in the field, to concrete cured in a lab at a specified constant temperature. So that's what that's what this particular maturity function would do. Compare concrete cured at a specified temperature to whatever your concrete, the time and temperature conditions out in the field. That function's a little bit more difficult. It's not used very often, but here's our equivalent age. And here we've got this summation, and we've got kind of this funky exponential factor right here. So this is a nonlinear equation. And here's your delta T. So Q is the activation energy divided by the gas constant. The ASTM tells you how to get that activation energy, very similar to, or also using 2x2-inch cubes. T sub A, same thing here. Average temperature during your time. This is in Kelvin. This activation energy is also in Kelvin. Specified temperature T sub S. That's your laboratory curing temperature, right? Again, that's in Kelvin. And then your time interval is in hours. This equation is not used very often, mainly because I think it's not understood very well. It's based on the Arrhenius equation, and the Arrhenius equation, for us chemistry geeks out there, that predicts the rate of a reaction, of a chemical reaction, which is essentially what's happening here. As the cement's hydrating, it's a chemical reaction. So, but anyway, again, this equation is just not used very often. So how do we apply this maturity method? First thing we do is we cast and cure a minimum of 15 cylinders in the lab. This is this is done in the lab, and it's got to be the same mix that's used in the field. So if you got a 5,000 psi mix, you want to load it early, and you want to estimate what the strength is. First thing, using the maturity method, the first thing you got to do is establish this maturity curve in the lab by casting these 15 cylinders. We put maturity cylinders in at least 2 of the cylinders, that measures our time and temperature. And then we test a couple of cylinders, at different ages, 1, 3, 7, 14, 28 days. Maybe we're testing them more frequently for a high early mix, or maybe we're testing them even more frequently, depending on when you want to load them. And then you plot the compressive strength against the maturity index, and you get something that looks like this. Again, down here, x-axis, the maturity is, again, simply the temperature multiplied by the time. And then each time we break a cylinder, we figure out what that maturity value is, and then we plot the compressive strength. So as it starts to age, our compressive strength goes up, gets to a certain point, and that reaction rate, that strength development starts to slow down. And then to apply it in the field, we've established that maturity index, which is a graph, the previous graph. We take maturity sensors prior to placement, put them at critical locations, maybe in a pier or footing or something like that. And then we monitor that maturity sensor as the concrete cures. And if we want to figure out what the strength is at 7 days, we download that sensor. We see where our maturity falls on this line, and then we figure out what the compressive strength is. That's an estimate. If you're doing some critical loading operation, maybe you don't want to rely solely on this maturity method. Maybe you want to put some field cure cylinders out there. Maybe you want to do some other non-destructive testing, maybe a rebound hammer or Windsor probe, or maybe you want to take cores if that's an option. But the biggest takeaway here is to do the maturity method. It starts in the laboratory. So it's a great method. We've used it a number of times, and it's proven to be pretty valuable to a lot of contractors. So, all right, we've got question number 4. It should read something like, what are the 2 parameters that we measure for maturity functions? We've talked about that. So hopefully you remember.
Great, Steve, please continue.
So time and temperature, those are the 2 functions those are the 2 parameters that we're measuring for the maturity function. And we've got one more question here. This is the last question. It's a true or false question. The equivalent age maturity function assumes that concrete strength gain is linear based on time and temperature. For those that don't remember that equivalent age maturity function, that's the one that is based on the Arrhenius equation. And that's the only hint I'm going to give you.
All right, Steve, go ahead.
So that answer is false, again, based on the Arrhenius equation, and that is definitely not linear. So that brings us to the end of the presentation. Not sure if any questions came in or not. If they did, I'll answer as many as I can.
Yes, we have one. After protection is removed and surface temperature returns to ambient, say less or much less than freezing, where heat of hydration slows or stops, does the heat of hydration start up again with associated strength gain? After ambient concrete temp comes back up to 40+ degrees. In other words, if strength doesn't come up to design strength, is there any way to jumpstart it again?
That's a great question. and I've had a couple of real world applications where we've shown that to be true, where we've had some low cylinder breaks, and we had field cure cylinders. We had a lot of field cured cylinders because it was kind of an accelerated project, although not the one I've been referencing. And the strength slowed down significantly. And when the temperatures started to get warmer again, those field cured cylinders, they did start to see some strength gain. So the answer is yes, but the most important thing is to make sure that you've got adequate protection during that protection period. The 3 days, 6 days, or whatever that protection period is. If you've got adequate protection during that period, then yes, we would expect to see, and we have seen, strength development continue when the weather gets warmer, when temperatures get warmer. That's a great question.
Steve, what temperature range, people are sending in questions in just a second. What temperature range can you get from glycol?
I'm trying to remember. We were seeing surface temperatures in the mid 60s, but that is a big function. So the temperatures can be adjusted on those glycol heaters, where maybe you put it up to like 95 or something like that. But we never measured the actual temperatures of the glycol solution itself, but we were seeing surface temperatures in the 60s. But they had a lot of blankets on there. I think that answers the question.
Oh, sorry. What is the comparison between Celsius and Kelvin temperatures? I'm not sure.
Oh, I think it's 273 degrees. So I think you subtract 273 degrees from Celsius. Somebody's going to say that that's not right, but it's something like that.
How does ACI or an engineer assess the effects of precipitation, cold rain, for instance?
Precipitation and rain and wind do not play a factor. It's just surface temperature. So I guess it would play a factor if the cold rain were to drop the surface temperature. But hopefully we're protecting it. Hopefully there's a blanket on it. Hopefully it's not being exposed to rain during that protection period. But that's how it would affect it, is by dropping that surface temperature, which we wouldn't want to see.
Can you please expand on the differences in cold weather definition? 3 consecutive days, average temp below 40 versus air temperature has fallen to or is expected to fall below 40 during the protection period.
I'm trying to scroll back. Read the question again, Howard. I'm sorry.
Please expand on the differences in cold weather definition. 3 consecutive days average temp below 40 versus air temperature has fallen to or is expected to fall below 40 during the protection period.
Yeah, I'll be honest, I'm not wild about these two definitions, because we don't always know if it's going to fall below 40, and we don't always know what that average is going to be. I mean, if you plan for not having cold weather, because you're looking at the weather forecast and it doesn't look like it's going to get, the average is going to get below 40. It's not going to be below 50, and it happens to get below 40 or below 50. Then you're kind of in a bit of a pickle. The differences are slight. But it's better to err on the side of caution. If you're getting temperatures, you start to get temperatures below 40 regularly, then you really need to start considering cold weather measures. I mean, the definition is fairly clear between the two, although there's a little bit of rolling the dice with both of them.
And then Kelvin and Celsius is 273 degrees.
Okay.
And that does it. That brings us to the end of our time and the end of the questions.
Okay. I want to let everybody know that we do have another presentation coming up. I believe it is next week. Sorry for quickly scrolling through like this. Wow, it just went away completely. October 28th, corrosion of embedded steel reinforcement and hardened concrete. And it'll be presented by Chris Kelson and myself. So you'll get to hear me again for another 20 or 30 minutes. That's October 28th. The information from registration from this webinar, you should be able to use that for the next one, although it might be a different link, but should be in the same document that you got.
All right, thank you everyone.
Okay.
That concludes our presentation for today. Have a great afternoon.
Thank you.